At the heart of a distant elliptical galaxy called NGC 5419, astronomers have uncovered something remarkable: not one but two supermassive black holes sharing the same galactic core. Their combined gravity shapes the star's gas, and even the future of the galaxy itself, hinting at a violent history of mergers and collisions. Today we explore what makes this dual black hole system so extraordinary. If you enjoyed journeys into the deep universe, please like, subscribe and share, and tell us in the comments, what would you ask about a galaxy that hides two giants at its center? Thank you for watching. Now, let's begin. In the nearby universe, galaxies often gather into loose groups and poor clusters, rather than existing alone, and the region around NGC 5419 is one of these environments. The galaxy belongs to the NGC 5488 group, which contains a modest number of members and forms a gravitationally bound system of galaxies embedded in a larger halo of dark matter. On an even broader scale, NGC 5419 is also recognized as the brightest cluster galaxy of the system, catalogued as Abell S 0753, a poor galaxy cluster whose mass is dominated by dark matter, but that also contains hot diffuse gas and numerous satellite galaxies. Seen at a distance of roughly 200 million light-years, this part of the universe lies well within the local cosmic neighborhood, yet it already illustrates the way structure builds up hierarchically from single galaxies to groups and clusters. The galaxies in such a system occupy a volume spanning several million light-years, bound together by their shared gravitational potential and slowly evolving over cosmic time as smaller structures fall in and merge. The cluster environment around NGC 5419 is shaped not only by the visible galaxies, but also by the intragroup and intracluster medium, a very tenuous plasma that fills much of the space between galaxies. This hot gas at temperatures of tens of millions of degrees Celsius emits X-rays that trace the underlying gravitational well. Observations show extended X-ray emission centered on NGC 5419, indicating that the galaxy sits close to the bottom of the cluster potential, where the gas density is highest. In a poor cluster, like Abell S 0753, the X-ray luminosity and gas mass are lower than in the richest clusters, but the same basic components are present: a central concentration of hot gas, a population of galaxies orbiting within a common halo, and a reservoir of dark matter that provides most of the gravitational binding. The hot plasma interacts with galaxies that move through it, stripping gas from some and altering their star formation histories, while radio observations of diffuse emission in this system reveal that energetic particles and magnetic fields are also present on scales of hundreds of thousands of light-years. Within the wider group and cluster galaxies follow orbits that respond to the combined mass of dark matter, gas and stars. Their velocities, typically of the order of hundreds to more than 1,000 kilometers per second in such systems, provide one of the main tools for estimating the total mass of the cluster. In Abell S 0753, the observed dispersion of galaxy velocities places it firmly in the regime of poor clusters, with fewer galaxies and lower overall mass than massive rich clusters, but still much more massive than a single large galaxy. The brightest cluster galaxy, in this case NGC 5419, usually lies close to the center of both the galaxy distribution and the X-ray emitting gas. Its position marks the approximate minimum of the gravitational potential around which other group and cluster members orbit. Over long timescales, this configuration is maintained by a balance between the random motions of the galaxies and the pull of gravity from the dark matter halo and hot gas. From a cosmological point of view, the NGC 5488 group and Abell S 0753 are part of the cosmic web, the large-scale network of filaments and nodes formed by gravitational collapse of matter in the universe. Groups and poor clusters like this one act as intermediate mass scales that bridge the gap between isolated galaxies and the richest clusters. Their properties, including galaxy content, gas temperature, and total mass, follow trends seen across the full range of environments. The presence of an extended X-ray halo centered on NGC 5414 shows that the system has already assembled enough mass to confine hot gas for long periods, while the classification as a poor cluster indicates that its galaxy population is more modest than that of large, very rich clusters. In this setting, smaller galaxy associations may continue to fall in, along surrounding filaments, gradually increasing the mass of the system. The details of these accretion processes fall outside the scope of this narrative, but the important point for understanding NGC 5419 is that the galaxy resides in a mature, gravitationally relaxed environment rather than in isolation. On the sky, this entire system appears within the southern constellation Centaurus. Deep optical imaging reveals a dominant central elliptical galaxy, NGC 5419, surrounded by fainter galaxies, whose distribution roughly traces the projected shape of the underlying group and cluster. Radio maps show an extended low surface brightness relic source, PKS B1400-33, offset from the cluster center, yet still associated with the same environment, an indication that energetic events have taken place in the recent past, and that the intra-cluster medium is capable of preserving aged radioplasma. X-ray data add a further component by mapping the diffuse hot gas that envelopes the galaxies and smooths out small-scale irregularities in the gravitational field. Taken together, these observations build a consistent picture. NGC 5419 is the dominant galaxy in a poor cluster, with a detectable intracluster medium sitting near the center of the gravitational potential, well surrounded by satellite galaxies, old radioplasma, and a bath of hot thin gas. In this outermost view, the internal structure of NGC 5419 remains unresolved. The galaxy is treated as a single luminous body defining the center of the system. The focus stays on the cluster scale, where the key ingredients are the population of galaxies, the dark matter halo, and the intracluster gas. This level of description establishes the environmental context needed to interpret the properties of the central galaxy in later, more detailed stages. In a poor cluster, such as Abel S 0753, which hosts NGC 5419, as its brightest cluster galaxy, the visible galaxies represent only a small part of the total mass and of the physical content of the system. The cluster contains a few tens of known galaxy members, including NGC 5419 and other luminous galaxies catalogued in the NGC and ESO surveys, spread across a region spanning several million light-years. Their light traces some of the baryonic matter, but most of the mass resides in dark matter and in the hot intracluster medium. Dark matter provides the dominant gravitational potential, amounting in typical galaxy clusters to roughly 3/4 or more of the total mass, while the hot plasma contributes around 1/10 to 1/5, and the stars in galaxies contribute only a few percent. The Abel S 0753 system follows this general pattern. The galaxies, the X-ray emitting gas, and the dark matter together define a common halo whose gravitational field binds the system. The hot intracluster medium is a very diffuse plasma with particle densities of only a few thousand particles per cubic meter, yet it extends over hundreds of thousands to millions of light years and reaches temperatures of tens of millions of degrees Celsius. At these temperatures, the gas emits X-rays by Bremsstrahlung and line emission from heavy elements, and X-ray observations detect an extended glow centered on NGC 5419. The approximate symmetry of this X-ray emission around the central galaxy indicates that the gas is close to hydrostatic equilibrium, meaning that the pressure gradient in the plasma balances the gravitational pull of the cluster mass. Under this assumption, astronomers can use the radial profiles of gas temperature and density to infer the total mass as a function of radius, obtaining values characteristic of poor clusters of the order of several 100 trillion solar masses. In this mass range, the characteristic velocities of galaxies orbiting within the cluster potential are of the order of several hundred to about 1,000 kilometers per second, consistent with the measured redshifts and velocity dispersion of the member galaxies in the NGC 5488 group. The galaxy population itself shows the environmental trends typical of dense regions in the nearby universe. Close to the center, bright elliptical and lenticular galaxies dominate, including NGC 5419, while fainter disk galaxies tend to occupy larger projected radii and less dense regions. Repeated tidal encounters, mergers, and the removal of cold gas by ram pressure in the intracluster medium over long timescales contribute to building up this pattern, which is often called the morphology-density relation, and describes how galaxy type depends on local density. The stars that reside in these galaxies contribute to the overall baryonic mass budget, but their combined mass is still significantly smaller than that of the hot intracluster gas. In addition to the gas directly associated with the galaxies and the smooth intracluster medium, there is also likely to be intracluster starlight formed from stars that have been tidally stripped from their parent galaxies and now orbit freely in the cluster potential. This diffuse stellar component can be important in the total light budget of poor clusters, though its detailed distribution in Able S0753 has not been mapped in the same depth as in some richer systems. Radio observations show further evidence for the interplay between galaxies and the intracluster medium in this environment. The low surface brightness radio source PKS B1400-33 appears as an extended filamentary relic offset from the central X-ray emission that is centered on NGC 5419. Its morphology and very steep radio spectrum indicate aged synchrotron plasma likely injected in the past by radio jets from one of the cluster galaxies and then displaced and shaped by motions in the intracluster gas. The presence of such a relic in a relatively low-mass cool cluster is unusual because most known radio relics reside in more massive merging clusters, but in this case the relic still traces energetic processes that have taken place within the shared gaseous environment. The combined picture of galaxies' hot plasma and dark matter can be described in terms of a common potential well with multiple traces. The galaxies move on orbits determined mainly by the dark matter halo. The hot gas sits in approximate hydrostatic equilibrium within the same potential and responds to any recent disturbances, and the radio relic preserves a record of past energetic activity that has interacted with the gas. On scales comparable to the characteristic radius where the cluster is gravitationally bound, often called the virial radius, the dark matter halo is thought to follow a smooth centrally concentrated profile, while the galaxies and gas provide more clumpy traces of the same mass distribution. Measurements of the galaxy velocity dispersion, the extent of the X-ray emitting gas, and the surface density of galaxies together suggest that Able S0753 is dynamically relatively relaxed without the strong substructure and temperature variations that mark violent recent mergers in richer clusters. In such a state, individual galaxies continue to orbit within the common halo, gradually losing orbital energy through dynamical friction if they are massive and slowly contributing stars and gas to the intracluster components through interactions. The long-term effect is to increase the contrast between the central brightest cluster galaxy and its surroundings, and to build up the extended intracluster medium and intracluster light that characterize group and cluster environments at the present epoch. In a nearby universe context, when astronomers describe the place of NGC 54119 in the sky and in space, they refer both to its position on the celestial sphere and to its distance in the expanding universe. The galaxy lies in the southern constellation Centaurus south of the celestial equator, so it is better placed for observation from southern latitudes than from most locations in the northern hemisphere. Its equatorial coordinates in the standard J2000 system correspond to a right ascension of about 14 hours and a declination of roughly -34 degrees, placing it among a rich background of Milky Way stars and other external galaxies in this part of the sky. In deep optical surveys, the field around NGC 54119 shows a smooth, nearly round glow for the galaxy itself, with numerous fainter galaxies scattered across scales of tens of arc-minutes, many of which belong to the same group and cluster environment. The projected angular size of NGC 54119 on the sky is of the order of 4 by 3 arc-minutes, so its apparent extent is comparable to that of many other bright nearby galaxies. At a visual magnitude around 11, the galaxy is not visible to the unaided eye, but can be detected with moderate amateur telescopes under dark skies, where it appears as a diffuse elliptical patch rather than as a detailed structure. From the point of view of physical distance, NGC 54119 belongs to the nearby universe on cosmological scales, but lies well beyond the local group and the other small associations of galaxies that surround it. Its measured redshift, which quantifies the fractional shift of spectral lines toward longer wavelengths due to cosmic expansion, is approximately 0.014. Interpreted with the standard value of the Hubble constant, this redshift corresponds to a distance of about 64 megaparsecs, or roughly 210 million light-years. Uncertainties in the exact value arise from both measurement errors and from the contribution of a local peculiar velocities, which are motions of the galaxy relative to the smooth Hubble flow caused by the gravitational pull of nearby structures. Correcting for these effects yields a distance estimate in the same general range, so for descriptive purposes, it is accurate to say that NGC 54119 lies at a distance of a little over 200 million light-years. At that distance, 1 arc-minute on the sky corresponds to a physical scale of roughly 20 kiloparsecs, so the observed angular size of a few arc-minutes translates to a physical diameter of the order of 100 to 130 kiloparsecs. This makes NGC 54119 significantly larger in linear size than typical spiral galaxies like the Milky Way, which have characteristic disk diameters of several tens of kiloparsecs, and places it firmly in the class of massive elliptical galaxies with very extended stellar envelopes. Its total luminosity in the visual band corresponds to an absolute magnitude of roughly -23, a value characteristic of bright early-type galaxies that dominate the light of their host groups and clusters. In practical observing terms, NGC 54119 is a target best studied with professional telescopes that can resolve its inner structure and measure its kinematics, but its basic appearance as a bright elliptical galaxy can be confirmed with smaller instruments. Long exposure images with large ground-based telescopes and with survey facilities show a smooth radial decline of surface brightness from the center outward, with weak deviations from perfect ellipticity that reflect the orbital structure of the stars and any residual signatures of past interactions. The outer parts of the galaxy blend gradually into the intra-group and intra-cluster light, making it challenging to define a sharp edge to the system. Astronomers typically adopt an isophotal radius defined by a chosen surface brightness level as a practical measure of size, and for NGC 54119, such definitions lead to estimates of the order of 100 kiloparsecs for the extent of the main stellar body. The observational context is not limited to optical imaging. Infrared surveys detect the same smooth stellar distribution with colours that indicate an old metal-rich stellar population. Radio observations at centimetre wavelengths reveal a compact or moderately extended radio source at the position of the galaxy, consistent with low-level nuclear activity in the central regions, while wider field maps pick up the much larger offset radio relic that resides in the same cluster environment but not coincident with the galaxy itself. X-ray images from satellites show that the peak of the diffuse intracluster emission coincides closely with the position of NGC 55419, reinforcing its identification as the central and brightest galaxy of the cluster. Spectroscopic observations provide further constraints on its distance and on its motion relative to the cluster as a whole. By measuring the redshifts of absorption lines in the integrated stellar spectrum of NGC 5419 and of other cluster members, astronomers determine both the systemic velocity of the galaxy and the velocity dispersion of the cluster. For NGC 54119, the radial velocity inferred from its redshift is about 4,000 km per second in the cosmic microwave background frame, consistent with its position in the nearby Hubble flow. The scatter of velocities among the cluster members yields a velocity dispersion of several hundred kilometers per second, characteristic of a poor cluster, and consistent with the mass implied by the extent and temperature of the hot X-ray emitting gas. These measurements tie together the sky position, the distance, and the dynamical context of NGC 54119 in the low redshift universe. When NGC 54119 is treated as a single object, rather than as part of its group and cluster environment, it is classified as a massive early-type galaxy, with an elliptical morphology and a smooth extended stellar distribution that lacks the spiral arms and prominent dust lanes seen in many disk galaxies. In deep optical images, its light forms nearly concentric isophotes, which are contours of constant surface brightness on the sky that are close to elliptical in shape and show only mild variations in ellipticity and position angle with radius. The overall axial ratio measured from these isophotes indicates that the galaxy is only moderately flattened, consistent with the three-dimensional structure that is triaxial rather than perfectly spherical or strongly disk-like. From the radial surface brightness profile, which follows the average intensity of light as a function of distance from the center, astronomers find that NGC 549 is well described on large scales by a high-index Cercic profile, a flexible generalization of the de Vaucouleurs law that has long been used to model elliptical galaxies. A high Cercic index means that the central regions are relatively concentrated, while the surface brightness falls off slowly at large, radii producing an extended luminous envelope that blends into the intragroup and intracluster light. The effective radius, defined as the projected radius that encloses half of the total light of the galaxy, is of the order of several tens of kiloparsecs, with detailed photometric studies giving values in the approximate range from 20 to 30 kiloparsecs depending on the band and on the treatment of the outer envelope. Combined with the total luminosity, this large effective radius places NGC 55419 among the most massive and extended elliptical galaxies in the nearby universe. The galaxy's classification as an early type system reflects not only its morphology, but also its internal dynamics and stellar content. Stellar kinematic measurements along multiple position angles indicate that the galaxy falls in the category of slow rotators, where the ordered rotation velocity is small compared with the random velocities of the stars. The line-of-sight velocity dispersion, which quantifies the spread of stellar velocities along the observer's line of sight, remains high over a significant fraction of the effective radius, with values of several hundred kilometers per second. This high dispersion suggests a deep gravitational potential dominated by the combined mass of stars and dark matter, and is a standard signature of very massive elliptical galaxies. The relatively low ratio of rotation to dispersion, together with the modest ellipticity, implies that the flattening is largely supported by anisotropy in the stellar orbits, rather than by coherent rotation. In other words, stars in NGC 5419 move on a wide variety of three-dimensional orbits that collectively produce the observed shape and kinematics, a behavior typical of giant ellipticals that have experienced complex merger histories. Photometric and spectroscopic studies of the light from NGC 5419 show that its stellar population is dominated by old stars with ages of several to many billions of years, and with metallicities at or above the solar value in the central regions declining somewhat with radius. The colors of the galaxy in optical and near-infrared bands are red, indicating little or no current star formation, and a dominance of evolved low-mass stars on the main sequence and in later evolutionary stages. Spectral absorption, features that are sensitive to age and chemical composition, such as those associated with magnesium and iron, indicate that the stars formed relatively early in the history of the universe, and that enrichment by previous generations of stars has raised the abundance of heavy elements. The absence of strong emission lines from ionized gas in the integrated spectrum confirms that the current star formation rate is very low. Any cold gas content is correspondingly small as expected in a dense environment, where mechanisms such as ram pressure stripping tidal interactions and feedback from active galactic nuclei act over long timescales to remove or heat gas that could otherwise form new stars. On large scales, therefore, NGC 5419 fits comfortably into the observed correlations between stellar mass size kinematics and stellar population properties for massive early-type galaxies. It lies on or near the fundamental plane, which is an empirical relation among effective radius surface brightness and velocity dispersion for elliptical galaxies reflecting a form of virial equilibrium with systematic variations in mass-to-light ratio. Its high luminosity and large effective radius make it an outlier compared with typical field ellipticals, but similar to other brightest cluster galaxies, which often have extended envelopes and large stellar masses built up through repeated mergers and the accretion of satellite galaxies. The outer light profile shows evidence of excess luminosity at large radii, compared with a simple Cercic model fitted only to the inner regions, consistent with the presence of a CD-style envelope, which is an extended diffuse component commonly seen around central galaxies in clusters and groups. This envelope likely arises from stars that have been stripped from other galaxies during past interactions, and now orbit in the common potential centered on NGC 5419. Within the effective radius, the photometric structure remains smooth and lacks the strong isophotral twists, shells, or tidal tails that would signal very recent major disturbances, suggesting that although NGC 5419 has grown through mergers, its last major episode of violent relaxation is not extremely recent on cosmological timescales. When viewed as a complete system on whole galaxy scales, NGC 5419 is therefore a massive, slowly rotating red elliptical galaxy with a high stellar velocity dispersion, a large effective radius, and an extended luminous envelope, all of which are characteristic of central galaxies in mature group and cluster environments. At radii beyond the effective radius of NGC 5419, the stellar distribution becomes progressively more diffuse and gradually transitions into the extended halo and outer envelope that surround the main body of the galaxy. In deep images obtained with large ground-based telescopes, the surface brightness at these distances falls to very low levels, requiring careful treatment of the sky background and of scattered light to measure reliably. But the data show that there is still a significant amount of starlight out to tens of kiloparsecs beyond the half-light radius. The radial surface brightness profile in these regions deviates from a simple inward extrapolation of the Sirsic fit derived for the main galaxy body, with an excess of light at large radii that is characteristic of the extended envelopes of brightest cluster galaxies. This excess component has a very low surface brightness, but contains a substantial fraction of the total stellar mass when integrated over the large volume it occupies. Its presence indicates that NGC 5419 has accreted material from other galaxies over long timescales, with stars that once belonged to satellites now orbiting in the common potential, centered on the galaxy and its dark matter halo. The stellar color in the outer halo is typically somewhat bluer than in the inner regions, suggesting that the accreted stars often come from less massive systems with slightly lower metallicities, but the exact gradient depends on the detailed merger history. Kinematic studies that measure the line-of-sight velocities of stars or discrete tracers such as planetary nebulae or globular clusters at large radii provide important constraints on the mass distribution in these outer parts. For NGC 5419, the stellar light becomes too faint at large distances from the center for detailed stellar kinematics to be measured easily with current instruments. So most information about the halo dynamics comes indirectly from the photometric structure and from comparison with similar brightest cluster galaxies where outer kinematics have been obtained. In general, the velocity dispersion profile of massive ellipticals tends to decline more slowly with radius than would be expected if the stellar mass alone provided the gravitational potential, indicating the growing importance of the dark matter halo at large radii. In some systems, the dispersion even flattens or rises in the outer regions, a sign that the dark matter halo is dominant there. NGC 5419 is expected to follow the same pattern, given its high total mass and its role as the central galaxy in a poor cluster with a substantial dark matter component. Theoretical models and numerical simulations of galaxy formation show that the outer stellar halo of a central galaxy in a group or cluster is built mainly from stars stripped during minor and major mergers, with tidal debris dispersed over wide ranges of radius and orbital inclination. This process naturally produces an extended, roughly spheroidal envelope with a density profile that is shallower than that of the inner galaxy, and often exhibits substructure at very low surface brightness levels such as streams and shells, although these may be difficult to detect in a system like NGC 5419, where the line of sight passes through a crowded field of foreground stars and background galaxies. Superimposed on the diffuse halo light is a population of globular clusters, which are compact old star clusters that act as valuable tracers of the outer mass distribution. Massive elliptical galaxies and brightest cluster galaxies typically host rich globular cluster systems, with total numbers reaching tens or even hundreds of thousands of clusters. While detailed studies of the globular cluster population of NGC 5419 are less extensive than for some well-known central galaxies, it is reasonable based on its luminosity and environment to expect a large system of clusters extending to large radii. These clusters are easier to detect individually than diffuse halo light because they are compact and relatively bright, so wide-field imaging and spectroscopy can measure their spatial distribution and kinematics. In many massive ellipticals, the globular cluster system is divided into at least two broad subpopulations distinguished by color, which reflects metallicity, a metal-poor bluer component that is more spatially extended, and a metal-rich redder component that is more concentrated and closely follows the stellar light of the main galaxy. The metal poor clusters in particular trace the outer halo and can provide constraints on the dark matter halo profile and on the accretion history. For NGC 5P419, by analogy with other brightest cluster galaxies, a similar bimodal globular cluster system is likely, with the metal poor clusters extending well into the cluster potential and overlapping with the intracluster globular cluster population that is not clearly bound to any single galaxy. In the outer halo, the orbits of stars and clusters are predominantly controlled by the combined mass of the dark matter halo and the extended stellar envelope rather than by the detailed structure of the inner galaxy. The dark matter halo that surrounds NGC 5419 and its host cluster is expected to follow a roughly Navarro-Frank-White-like density profile with a central concentration and a slowly declining density, with radius beyond a scale radius of the order of a few hundred kiloparsecs. Within this context, the stars at radii of tens to a few hundred kiloparsecs sample the inner parts of the halo, where the potential is deep but already significantly influenced by dark matter. Their motions, if measured, would reveal velocity dispersions that reflect this potential, helping to separate the contributions of stars and dark matter to the total mass. The presence of an extended stellar halo and globular cluster system therefore provides not only an observational signature of the past merger history of NGC 5418, but also a practical tool for probing its mass distribution on scales where direct measurements of the dark matter are otherwise difficult. In summary, at the level of the outer halo and extended stellar regions, NGC 5419 consists of a luminous main body embedded in a very faint envelope of stars and star clusters that stretches far into the surrounding cluster environment, with the detailed properties of this envelope shaped by a long history of accretion and by the underlying dark matter halo that governs the dynamics on these scales. Closer to the center of NGC 5419 at radii of a few kiloparsecs, the light distribution and the stellar motions change character compared with the outer halo and extended envelope. The surface brightness profile that describes the galaxy on large scales no longer follows a single Circic law all the way inwards, but instead shows a distinct break at a characteristic radius, where the slope becomes much shallower toward the center. Astronomers refer to this type of structure as a depleted stellar core and model it with a core Circic profile, which combines an outer Circic function with an inner power law of low slope. In NGC 5419, the break radius of the core defined photometrically as the point where the curvature of the profile changes has a value of about 1 1/2 arc seconds. At the distance of the galaxy, this corresponds to a physical size of a few hundred parsecs, roughly 400 to 500 parsecs, so the depleted region extends across almost half a kiloparsec. Inside this radius, the surface brightness increases only slowly toward the center, when compared with the inward extrapolation of the outer profile, meaning that the central stellar density is lower than would be expected if the galaxy had grown only through smooth dissipative processes. This low-density core places NGC 5419 among the class of massive core ellipticals, which are luminous early-type galaxies with central light deficits linked to their merger histories. When the observed inner profile of NGC 5419 is compared with the outer Circic fit, the difference in luminosity can be interpreted as a stellar mass deficit, that is, the amount of stellar mass that appears to be missing from the center relative to the expectation from the outer structure. Empirical studies of many core ellipticals show that these mass deficits typically amount to a few times the mass of the central supermassive black hole, and are thought to arise when stars are scattered out of the very center by the gravitational influence of one or more black holes during and after galaxy mergers. In this framework, the size of the depleted core in NGC 5419 is consistent with the presence of a central black hole, whose mass is of the order of several billion to about 10 billion solar masses, in line with dynamical mass estimates that fit the inner stellar kinematics. Within the inner kiloparsec, the kinematic structure of NGC 5419 displays features that are common in massive early-type galaxies, but that also show some distinctive patterns. Integral field spectroscopy reveals that the galaxy is dominated by random stellar motions rather than by ordered rotation, with a line-of-sight velocity dispersion of roughly 350 km per second that remains nearly constant across most of the low-surface brightness core. The mean rotation velocity stays well below 50 km per second on these scales, so the ratio of ordered to random motion is low, and the inner regions belong firmly to the class of slow rotators. Despite the low amplitude of the rotation, there is a kinematically distinct core in the central few kiloparsecs. The inner region rotates in the opposite sense to the outer galaxy. A kinematically distinct core is a central zone in which the mean stellar velocity field shows a clear change in orientation or sign relative to the rest of the galaxy, indicating that at least part of the inner stars occupy orbits that are decoupled from the bulk of the system. In NGC 5419, this counter-rotating pattern extends over a spatial scale, comparable to several times the core radius, and points to a formation history that has involved one or more mergers, bringing in stars with different angular momentum directions. Dynamical models that reproduce both the photometric profile and the two-dimensional velocity and dispersion fields use large libraries of stellar orbits in a triaxial gravitational potential. For NGC 5419, such models show that the orbital distribution in the very center is close to isotropic, meaning that stars have nearly equal amounts of motion in the radial and tangential directions, while the outer parts of the core and the regions beyond are more anisotropic. This is notable because many core ellipticals show a strong tangential bias in their innermost orbits, interpreted as a signature of long-term scouring by a hard central black hole binary that has ejected stars on radial orbits. Recent numerical simulations of dry mergers between massive galaxies, that is, mergers in which little cold gas is present, suggest a two-phase picture for the build-up of cores. In this picture, an initially isotropic core forms as massive black holes sink toward the center by dynamical friction, following a merger with the core size set by the combined mass of the black holes and by the details of the merger orbit. Only after a hard binary has formed and had time to interact with many stars does the orbital structure become strongly tangential. The nearly isotropic center of NGC 5419, together with its well-developed depleted core and its slow rotation, matches the conditions expected in these models for a massive elliptical galaxy in an early or intermediate stage of core evolution. On inner kiloparsec scales, the gravitational potential that controls the stellar motions arises from the combined mass of the stars, the dark matter halo, and a central black hole with a mass of several billion solar masses. But the contribution of the black hole becomes increasingly important toward the center, because its mass is concentrated within a very small volume. The high and nearly flat velocity dispersion profile across the depleted core, the presence of a kinematically distinct inner region, and the large size of the low-density center together characterize the inner galaxy and core region of NGC 541 at this stage. Within the inner kiloparsec of NGC 5419, the depleted stellar core and its surrounding regions form a continuous dynamical structure whose properties can be quantified by combining high-resolution photometry with spatially resolved spectroscopy. The core Sursic fit to the surface brightness profile provides two key scales: the break radius, which marks the transition from the steep outer Sursic profile to the shallow inner slope, and the radius at which the surface brightness deficit becomes significant relative to the extrapolated outer law. For NGC 5419, the break radius of about 1½ arcseconds, corresponding to a few hundred parsecs at the distance of the galaxy, defines the approximate size of the low-density core, while the luminosity deficit integrated within this radius yields a stellar mass deficit that can be expressed as a multiple of the central black hole mass. Empirical studies of similar core elliptical galaxies indicate that the stellar mass missing from the center typically amounts to a few times the black hole mass, with values between about 1 and 10 times, depending on the system and on the modeling assumptions. When NGC 5419 is placed on these relations using a black hole mass estimate of several billion solar masses derived from dynamical models, the inferred mass deficit falls within the scatter of the observed correlation, supporting the view that its core has been shaped by the interaction between central black holes and stars during one or more past mergers. To turn the observed two-dimensional light profile into a three-dimensional mass distribution, astronomers deproject the surface brightness under an assumed geometry, often axisymmetric or triaxial, and multiply by a spatially varying stellar mass to light ratio inferred from stellar population models. Spectroscopic measurements of line strengths that are sensitive to age and metallicity, combined with population synthesis, indicate that the stars in the inner regions of NGC 5419 are old and metal, rich with only modest radial gradients. This allows the mass-to-light ratio to be treated as approximately constant within the inner kiloparsec, so that the deprojected luminosity density can be used as a proxy for the stellar mass density. Adding a central point mass representing the black hole and an extended dark matter halo, whose contribution in the innermost regions is relatively small compared with that of the stars, and the black hole yields a complete gravitational potential in which the observed kinematics can be modelled. Integral field spectrographs provide two-dimensional maps of the line-of-sight velocity and velocity dispersion across the central few kiloparsecs sampled with spatial resolution better than 1 arcsecond. For NGC 5419, these data show a nearly flat velocity dispersion profile, with values around a few hundred kilometers per second across the depleted core, together with low mean rotation and a pattern of velocities that changes sign between the inner region and the outer galaxy. Orbit-based dynamical models such as triaxial Schwarzschild models use a superposition of many individual stellar orbits computed in the trial potential to reproduce both the light distribution and the kinematic maps. By adjusting the weights of different orbital families and varying the mass of the central black hole and the parameters of the dark matter halo, the models converge on a configuration that matches the observations. In the case of NGC 5419, such modelling indicates that the orbital distribution inside roughly 1 kiloparsec is close to isotropic, meaning that stars have similar amounts of radial and tangential motion, while outside this radius, the orbits become more anisotropic. The nearly isotropic inner structure is noteworthy because many core ellipticals show a strong tangential bias in their central orbits, a signature often attributed to long-term scouring by a hard black hole binary ejecting stars on radial orbits. In collisionless simulations of dry mergers between massive galaxies, a two-phase behavior emerges in the first phase. Supermassive black holes spiral toward the center under the action of dynamical friction and rapidly carve out a low-density core whose orbital structure remains roughly isotropic. In the second phase, once a bound binary has formed, repeated three-body interactions gradually remove stars on low angular momentum orbits and build up a tangentially biased center. The combination of a well-developed depleted core and an almost isotropic central orbit distribution in NGC 5419 is consistent with this picture of a system in which the first phase of core formation has taken place, but the second slower phase has not yet fully reshaped the orbital structure. On scales of a few hundred parsecs to a few kiloparsecs, the mass budget in NGC 5419 is dominated by stars with a black hole contributing a significant but still minority fraction of the enclosed mass except very close to the center, and the dark matter halo contributing only weakly inside these radii. The high central velocity dispersion therefore reflects both the depth of the stellar potential and the additional concentration of mass at the very center due to the black hole. The fact that the dispersion remains nearly constant across the depleted core suggests that the phase space distribution of stellar orbits has adjusted to the combined potential in a way that maintains a roughly uniform second moment of the line of sight velocity. This uniformity, together with the smoothness of the surface brightness profile and the absence of strong non-axis symmetric features in the inner isophotes, indicates that the inner galaxy has reached a quasi-stationary dynamical state on these scales, even if its detailed orbital structure still carries the memory of past mergers. Within this inner depleted region, the gravitational potential is therefore set by a combination of the luminous mass traced by the smooth stellar light distribution, an extended dark matter component that becomes more important at larger radii, and a central black hole of several billion solar masses whose sphere of influence overlaps with the core. The structural and kinematic properties of this zone provide the necessary framework for understanding the still smaller nuclear region, where distinct central light concentrations and more complex kinematics are observed. But at the level of the inner galaxy and core region, they already identify NGC 5419 as a massive core elliptical, whose central structure bears the imprint of its assembly history and of the dynamical role of its central black hole. In the innermost few hundred parsecs of NGC 5419, the smooth depleted stellar core gives way to a nuclear region, whose light distribution shows clear substructure when observed with sufficient spatial resolution. High-quality imaging from space-based telescopes and from ground-based telescopes equipped with adaptive optics reveals that the central light is not dominated by a single sharply peaked nucleus, but instead contains at least two distinct local maxima in surface brightness embedded within the low-density core. These nuclear light concentrations are separated by a projected distance of order, a few tenths of an arc-second, which at the distance of NGC 5419 corresponds to several tens of parsecs. One of these peaks lies close to the overall photocenter of the galaxy, defined by the symmetry of the isophotes at slightly larger radii, while the other is offset, remaining within the depleted core but clearly displaced from the central symmetry point. The fact that both peaks are embedded in the shallow inner profile of the core indicates that they do not represent separate galaxies with their own extended envelopes, but instead are local enhancements within the central light distribution of NGC 5419 itself. Photometric profiles extracted along different position angles through the nucleus show that the inner light distribution cannot be described adequately by a single smooth function, but requires additional components or a non-axis symmetric structure to model the two peaks. The point spread function of the observations is carefully characterized to ensure that the apparent double structure is not an artifact of the imaging system or of atmospheric blurring, and the persistence of the two peaks in data from different instruments and epochs supports their reality as physical features of the galaxy. Spectroscopic observations targeted at the nuclear region using long-slit or integral field setups with high spatial resolution provide further information about the nature of these central light concentrations. The central spectral features show that the stellar populations at the positions of both peaks are old and metal-rich, similar to the surrounding core, and there is no evidence for strong star formation or for very young stellar populations that would imply recent intense nuclear starbursts. Weak emission lines from ionized gas may be present at low levels, but they do not dominate the nuclear light. At the photocenter, there is evidence for a low-luminosity active galactic nucleus, indicated by compact radio or X-ray emission, and by subtle spectral signatures such as weak emission line ratios, consistent with low ionization nuclear emission. But this activity is faint compared with that in luminous quasars, or powerful radio galaxies. The second nuclear light peak does not display strong additional emission that would mark it as an independent active nucleus in current data, but its stellar light and location within the core suggest that it is dynamically distinct within the potential well of the central regions. The velocity field in the inner few hundred parsecs resolved by adaptive optics, assisted integral field spectroscopy, reveals a pattern in which the stellar velocity dispersion rises toward the approximate positions of the nuclear light concentrations, with a particularly strong peak near the photocenter and elevated values in the region around the offset nucleus. This behavior differs from that expected purely from the smooth continuation of the core kinematics and points to concentrated mass associated with the nuclear region. The nuclear light peaks therefore coincide with zones where the gravitational potential is particularly deep, consistent with the presence of one or more supermassive black holes embedded in the depleted core. At this stage of the description, the emphasis remains on the observed properties of the nuclear zone, a large low-density core on scales of several hundred parsecs that hosts two distinct stellar light maxima, separated by tens of parsecs, one of which lies close to the photocenter and shows signs of weak nuclear activity, and both of which are associated with locally enhanced velocity dispersion in the surrounding stars. The depleted core itself maintains a shallow light profile that rises only slowly toward the center, indicating that a substantial amount of stellar mass has been removed or redistributed relative to an inward extrapolation of the outer Circic profile. The nuclear region is therefore structurally and kinematically distinct within the inner galaxy, marking the place where the central mass distribution departs most strongly from a simple, smooth, single nucleus configuration, and where the observational signatures of concentrated central mass become most evident. High-resolution observations of the center of NGC 5419 provide detailed information about the structure of the nuclear region that hosts the double nucleus. Imaging with the Hubble Space Telescope resolves the inner part of the depleted core and shows that the central light distribution contains a compact point source very close to the photocenter of the galaxy, and a second slightly more diffuse nucleus offset from this point. The projected separation between the two nuclei is about 1/4 of an arc-second, which at the distance of NGC 5419 corresponds to a physical distance of roughly 70 parsecs or a few hundred light-years. Both nuclei lie well inside the break radius of about 1 1/2 arc-seconds that defines the depleted core, so they are embedded within the low-density central region rather than standing out as separate galaxies with their own extended halos. The point source at the photocenter is unresolved at the instrumental resolution of a few tenths of an arc-second, and dominates the light within the innermost resolution element. Its colors and compactness are consistent with emission from a low-luminosity active galactic nucleus, in agreement with previous radio and X-ray detections of weak nuclear activity at the position of NGC 54419. The off-centered nucleus appears slightly more extended in the images, with a profile that can be approximated by a compact stellar component superimposed on the shallow background of the core. Its stellar population inferred from broadband colors and limited spectroscopic information is old and metal, rich similar to the surrounding core stars, so it does not correspond to a very young star cluster or to a recent starburst. Adaptive optics assisted near-infrared imaging and spectroscopy with instruments such as Symphony on large ground-based telescopes confirm and refine this picture, with a typical spatial resolution of about 0.2 of an arc-second. These data clearly separate the photocentric point source from the offset nucleus, and trace the stellar continuum and absorption lines across the inner few hundred parsecs. The near-infrared images again reveal two brightness peaks, with a similar projected separation to that seen in the optical data, and careful modelling of the point spread function shows that both structures are robust features rather than artifacts of the imaging process. Long-slit and integral field spectra centered on the nucleus provide two-dimensional maps of the line-of-sight velocity and velocity dispersion in this region, outside the immediate vicinity of the double nucleus within the depleted core, but at radii larger than a few times the separation of the nuclei, the velocity dispersion remains nearly constant, at values of about 350 km per second, in agreement with larger scale measurements. In the region that contains the two nuclei, however, the dispersion rises markedly, reaching peak values of about 420 km per second. The spatial correlation between the enhanced dispersion and the positions of the nuclear light concentrations indicates that the gravitational potential is significantly deeper in this zone than would be expected from the smooth continuation of the stellar mass distribution alone. The mean stellar rotation in the central region remains small compared with the dispersion with amplitudes below about 50 km per second, but the velocity field shows a sign change between the inner region and the galaxy at larger radii, so that the inner few kiloparsecs form a kinematically distinct core that rotates in the opposite sense to the outer parts. The double nucleus sits within this kinematically distinct zone, and the pattern of velocities and dispersions measured across it must be reproduced by any dynamical model that seeks to infer the mass distribution. Orbit-based models constructed using the stellar kinematics on scales larger than the separation of the nuclei and explicitly excluding the central region, where the double nucleus dominates, yield a mass for the central supermassive black hole of order, several billion solar masses with favoured values around 7 billion solar masses. These models show that the measured black hole mass is consistent with empirical correlations between black hole mass and core size in massive elliptical galaxies, and that it is largely constrained by the stellar motions outside the double nucleus region. The presence of the second nucleus introduces some systematic uncertainty, but comparisons between models with and without explicit treatment of the nuclear asymmetry indicate that this uncertainty does not strongly change the inferred total central mass. The combination of the large depleted core, the compact photocentric point source associated with the low luminosity active nucleus, the offset stellar nucleus at a separation of tens of parsecs, and the strong local enhancement of the stellar velocity dispersion together points to a concentration of mass on the scale of the double nucleus that is greater than can be accounted for by stars alone. High signal-to-noise integral field data from instruments such as MUSE, combined with triaxial dynamical modelling, further show that the central orbit distribution is nearly isotropic, while still accommodating the double nucleus structure and the kinematically distinct core. Taken as a whole, the imaging and kinematic constraints indicate that NGC 5419 hosts at least one supermassive black hole with a mass of several billion times the mass of the Sun at its centre, and that the most straightforward interpretation of the double nucleus and the associated velocity dispersion peak is that there are two supermassive black holes within the depleted core separated by about 70 parsecs and embedded in the same nuclear region, although the detailed configuration and dynamical state of this pair remain topics of ongoing observational and theoretical study. At the spatial scale defined by the double nucleus of NGC 54119, the observational constraints on the central mass distribution can be combined into a quantitative description of a candidate supermassive black hole pair embedded in the depleted core. High-resolution imaging establishes that the two nuclear light concentrations are separated in projection by about 1/4 of an arc-second, which corresponds to roughly 70 parsecs at the distance of the galaxy, so the putative black holes would reside well inside the several hundred parsec scale core, and significantly within the inner kiloparsec where the stellar mass dominates over the dark matter halo. Adaptive optics-assisted integral field spectroscopy shows that outside the central region containing the double nucleus, the stellar velocity dispersion remains nearly constant at about 350 km per second, whereas in the zone that encompasses the two nuclei the dispersion rises to peak values of order 420 km per second. This local increase in dispersion requires an enhanced gravitational potential on the same spatial scale as the double nucleus, and cannot be reproduced by models that include only a smooth stellar mass distribution without additional concentrated mass. Orbit-based dynamical models that fit the stellar kinematics on scales larger than the double nucleus, deliberately excluding the inner region where the asymmetry is strongest, yield a central black hole mass of around 7 billion solar masses, with quoted uncertainties of a few billion solar masses. This value is consistent with empirical correlations between core size and black hole mass in massive elliptical galaxies, and with the mass expected from the galaxy's position on scaling relations between black hole mass and velocity dispersion. When the enhanced dispersion in the region of the double nucleus is taken into account, the simplest interpretation is that each of the two nuclear light concentrations marks the location of a supermassive black hole, and that the total mass of the pair is of order several billion to about 10 billion solar masses. More recent triaxial dynamical models that use high signal-to-noise integral field data from instruments such as MUSE treat the nuclear region and the kinematically distinct core in a unified way. These models construct large libraries of stellar orbits in a triaxial potential that includes a chord stellar density profile, a dark matter halo, and a central point mass or masses representing the black holes. By varying the total black hole mass and the distribution of stellar orbits, the models reproduce both the observed surface brightness and the full two-dimensional maps of velocity and velocity dispersion. In these studies, the best-fitting models for NGC 5419 indicate a total central black hole mass of about 10 billion solar masses, with statistical uncertainties at the level of a few percent, and systematic uncertainties related to the assumed dark matter profile and orbital structure. The combined evidence from earlier and more recent modelling therefore converges on a very massive central concentration of order, 10 billion solar masses residing within the depleted core. Within the current resolution limits, the individual masses of the two putative black holes are not measured directly, but the roughly similar brightness of the two nuclear peaks in the stellar light and the symmetric distribution of the enhanced velocity dispersion around them favour a configuration in which the two black holes have comparable masses rather than an extreme mass ratio. The low mean stellar rotation at the centre, combined with the elevated dispersion and the nearly isotropic central orbital distribution inferred from the dynamical models, suggest that the orbital motion of the black hole pair is oriented largely in the plane of the sky rather than along the line of sight. In this geometry, even a bound binary with substantial orbital velocity would produce only small net line of sight velocity shifts at the positions of the nuclei consistent with the observed pattern of very low mean velocity but high dispersion in the innermost maps. The absence of strong non-stellar emission from the offset nucleus in current radio and X-ray observations indicates that if a second black hole is present, it is either radiatively inefficient or accreting at a very low rate, so that its direct electromagnetic signature is weak. The photocentric nucleus, which coincides with a compact radio and X-ray source, is identified as a low-luminosity active galactic nucleus associated with one member of the pair. From the point of view of the surrounding stars, the key property of the system is the total gravitational field produced by the combined mass of the two black holes and the central stellar component. Stars on orbits that bring them close to the nuclei experience strong gravitational accelerations, and repeated close encounters over long timescales can alter the orbital distribution and contribute to the maintenance of the depleted core by removing stars on low angular momentum trajectories. On scales of tens of parsecs, the binary is embedded in a background of old metal-rich stars that share the general properties of the inner core population, and no substantial cold gas reservoir or recent star formation is detected in current data. At the nuclear scale, the configuration of NGC 5419 can therefore be described as a large low-density stellar core containing two compact nuclear light concentrations separated by about 70 parsecs each, associated with a peak in stellar velocity dispersion, and together tracing a central mass of order 10 billion solar masses whose detailed partition between the two components and exact orbital parameters remain the subject of ongoing dynamical studies. At the smallest resolvable scales in NGC 5419, the combination of high-resolution imaging, integral field spectroscopy, and dynamical modeling allows a focused description of the central system as a candidate binary of supermassive black holes embedded in a depleted stellar core. The cored surface brightness profile, with a break radius of about 1 1/2 arc seconds or a few hundred parsecs, and the presence of two distinct nuclear light concentrations separated by roughly 70 parsecs, establish the basic geometric framework for this system. The photocentric nucleus coincides with a compact radio and X-ray source, consistent with a low-luminosity active galactic nucleus, while the offset nucleus is a compact stellar component with properties similar to the surrounding old metal-rich core population. Outside the immediate vicinity of these nuclei, the stellar velocity dispersion remains nearly constant at about 350 km per second across the core, whereas in the region that encompasses the double nucleus, the dispersion rises steeply to peak values near 420 km per second. Orbit-based dynamical models that fit the kinematics outside the double nucleus show that this behavior cannot be explained by the stellar mass distribution alone and require a central mass of several billion solar masses concentrated within the inner few hundred parsecs, consistent with a supermassive black hole of roughly 7 billion solar masses when the nuclear asymmetry is not explicitly modelled. More recent triaxial dynamical models that include the full two-dimensional kinematic information and allow for a more general orbital structure find that the total mass associated with the central black hole or black holes is close to 10 billion solar masses, with formal statistical uncertainties of less than 10% and additional systematic uncertainties related to the assumed dark matter, halo, and mass-to-light ratio. These models also show that the orbital distribution of stars in the innermost few hundred parsecs is nearly isotropic, with similar amounts of radial and tangential motion, even though the galaxy as a whole is a slow rotator with a kinematically distinct core on kiloparsec scales. This nearly isotropic central region is important because it links the detailed structure of NGC 5419 to theoretical models of core formation in massive elliptical galaxies. Collisionless simulations of mergers between gas-poor early-type galaxies that each host a central supermassive black hole, indicate that core formation proceeds in at least two phases. In the first phase, following a merger, the black holes from the progenitor galaxies sink toward the common center under the action of dynamical friction, which is a drag force that arises when a massive object moves through a background of stars and dark matter, creating an overdensity that exerts a gravitational pull in the opposite direction to the motion. This process transfers orbital energy from the black holes to the surrounding stars and produces a low-density stellar core with an approximately isotropic orbital distribution. In the second slower phase, once the black holes form a bound binary, at separations of the order of a few parsecs or less, repeated three-body interactions between the binary and passing stars gradually eject stars on low angular momentum nearly radial orbits. This black hole scouring process deepens and enlarges the core and drives the orbital distribution toward a tangential bias, in which stars preferentially occupy orbits with large angular momentum. The observational finding that NGC 5419 has both a well-developed depleted core and a nearly isotropic central orbit distribution indicates that the system is in an intermediate state in this sequence. The core has been carved out in the sense that the central stellar density is lower than expected from an inward extrapolation of the outer Circic profile, and the size of the core is consistent with the presence of a central mass of several billion to about 10 billion solar masses. At the same time, the lack of strong tangential anisotropy in the innermost orbits suggests that the second phase of long-term scouring by a hard binary has not yet fully reshaped the orbital structure. The double nucleus, with its separation of tens of parsecs and its association with a local peak in velocity dispersion, fits naturally into this framework as the observable manifestation of two supermassive black holes that have sunk into the shared core but have not yet coalesced into a single object. In such a configuration, the binary is still relatively wide, and its orbital decay is expected to be governed mainly by interactions with the surrounding stars and by any residual gas rather than by gravitational wave emission. Gravitational radiation becomes the dominant mechanism for orbital shrinking only when separations reach sub-parsec scales, at which point the binary would radiate low-frequency, gravitational waves in the nanohertz range targeted by pulsar timing arrays. Current pulsar timing array limits on continuous gravitational waves from individual supermassive black hole binaries in the local universe apply primarily to systems with total masses of at least 1 billion solar masses at separations where gravitational radiation is already important, and they do not yet provide direct constraints on binaries with separations of tens of parsecs, such as the candidate pair in NGC 5419. The central region of this galaxy thus represents an evolutionary stage in which the main observable signatures of the binary are dynamical: a depleted stellar core, a double nucleus with a separation of order, 70 parsecs, a strong local enhancement in stellar velocity dispersion, and a nearly isotropic orbit distribution in the innermost few hundred parsecs. These properties match the expectations from dry merger simulations for a massive elliptical galaxy in which two supermassive black holes have already sunk into a common core, but have not yet shrunk to the separations required for gravitational wave-driven inspiral-making NGC 5419, a useful empirical case for studying the link between galaxy mergers, core formation, and the assembly of very massive black holes at the centers of brightest cluster galaxies. The binary interpretation of the central system in NGC 5419 raises specific questions about how a pair of supermassive black holes with a combined mass of several billion to about 10 billion solar masses evolves from kiloparsec scale separations after a galaxy merger down to the observed projected separation of roughly 70 parsecs, and then toward the regime where gravitational wave emission becomes important. In theoretical models of dry mergers between massive early-type galaxies, the inward migration of the black holes proceeds in stages that depend on the dominant mechanism for angular momentum and energy loss at each scale. At large separations of order, a kiloparsec each black hole orbits near the center of its host stellar distribution, and the merger of the galaxies produces a common potential in which the black holes become massive perturbers moving through a background of stars and dark matter. Dynamical friction, which arises from the gravitational wake induced by each black hole as it moves through the stellar field, transfers orbital energy from the black hole to the stars, and causes the black hole to spiral inward on a timescale that depends on its mass, the ambient density, and the velocity dispersion. For the very massive black holes implied in NGC 5419 with individual masses of order, a few billion solar masses, the dynamical friction timescale from kiloparsec to 100 parsec separations is relatively short in comparison with the age of the universe in a dense galactic core, so the formation of a bound pair on scales comparable to the depleted core radius is expected in many merger histories. Once the black holes reach separations of order a few tens to a few hundred parsecs, as suggested by the observed double nucleus in NGC's 5419, the simple dynamical friction treatment becomes less accurate because the gravitational influence of each black hole overlaps significantly, and the stellar distribution responds to the combined potential. At this stage, the pair may already be bound, but its orbital parameters are not directly constrained by current observations. The continued shrinking of the orbit is then governed by a combination of dynamical friction from the remaining stellar background, gravitational interactions with stars whose orbits bring them into the region around the pair, and any coupling to gas if a cold gaseous component is present. In gas-poor systems like NGC 5419, where there is little evidence for substantial cold gas in the central regions, the stellar interactions dominate, and the evolution is often described in terms of loss cone dynamics. The loss cone is the region in phase space occupied by stars whose orbits bring them close enough to the binary that they can be ejected or strongly perturbed in three-body encounters. Each such interaction removes energy and angular momentum from the binary and transfers them to the star, which leaves the central region on a higher energy orbit. If the supply of stars in the loss cone is efficiently replenished by two-body relaxation or by large-scale torques in a non-spherical potential, the binary continues to harden steadily. If the supply is not efficiently replenished, the binary may experience a slowing of its orbital decay. At separations of order a parsec, a process sometimes called stalling. In massive core ellipticals, the shape of the gravitational potential and the presence of triaxiality can significantly enhance the feeding of stars into the loss cone, because box orbits and other centrophilic trajectories bring stars repeatedly close to the center without relying solely on slow collisional relaxation. Dynamical models of NGC 5419 that find a triaxial structure and a nearly isotropic central orbit distribution indicate that there are many stars whose orbits can interact with the central binary over long timescales, which supports the idea that evolution can continue beyond the tens of parsec scale, although the exact rate is not directly measured. When the separation between the black holes decreases to sub-parsec scales, gravitational wave emission becomes increasingly important as a mechanism for energy loss. At separations of a few thousandths of a parsec, a circular binary with a total mass of about 10 billion solar masses would radiate gravitational waves at nanohertz frequencies and merge on a timescale shorter than 1 billion years. The formation of such a compact binary from an initially wide pair involves passing through regimes where stellar hardening gas torques, if present, and gravitational waves all contribute to the orbital decay. For a system like NGC 5419, current observations only reach the regime where the two putative black holes are separated by tens of parsecs, so any later evolution toward gravitational wave-dominated in spiral is inferred from theoretical models rather than directly observed. The low level of nuclear activity and the absence of a strong cold gas reservoir in the centre imply that gas dynamical torques are unlikely to play a major role at present, so stellar dynamical processes remain the primary channel for further shrinking. In this context, the large depleted core of NGC 5419, whose size and mass deficit are consistent with the cumulative ejection of stars by the binary, indicates that a significant amount of interaction between the central mass and the surrounding stars has already taken place. The nearly isotropic central orbit distribution suggests that the system may still be in a phase where the binary has carved out the core and shared its energy with the stars, but has not yet reached the stage where the orbital configuration of the stars has been strongly reshaped toward tangential anisotropy by long-term scouring. Timescale estimates for this intermediate regime are uncertain and depend sensitively on the details of the stellar distribution, the degree of triaxiality, and any perturbations due to additional mergers or external torques. Simulations tailored to galaxies with core sizes and black hole masses similar to those inferred for NGC 5419 show that the time required for a binary at separations of order tens of parsecs to reach the gravitational wave regime can range from less than 1 billion years to more than a Hubble time, depending on how efficiently stars are supplied to the loss cone. In the absence of direct measurements of the orbital motion of the nuclei, or of other traces such as periodic electromagnetic variability, the current data for NGC 5419 do not distinguish between these possibilities. The observational picture thus describes a very massive central system that has already formed a large depleted core and a double nucleus at separations of tens of parsecs, consistent with an advanced stage of dynamical evolution following one or more dry mergers, while leaving open the question of how quickly the pair will proceed toward the compact binary stage where gravitational wave emission dominates its evolution. At the spatial scales where the two nuclear light concentrations of NGC 5419 are separated by tens of parsecs, the gravitational influence of the central mass dominates the dynamics of the surrounding stars. For a total black hole mass of order 10 billion solar masses and a stellar velocity dispersion of about 350 kilometers per second, the characteristic radius within which the enclosed mass of stars equals the black hole mass is of order a few hundred parsecs. This radius, often called the sphere of influence, is comparable to the size of the depleted core, which extends across several hundred parsecs. As a result, most of the stars inside the core move in a potential in which the mass of the black hole pair is at least as important as the stellar mass. And in the innermost tens of parsecs, the black holes provide the dominant contribution. In the absence of a binary, such a central concentration of mass would tend to produce a velocity dispersion profile that rises smoothly toward the center, reflecting the deeper potential well. In NGC 5419, the nearly constant dispersion of about 350 kilometers per second across much of the core, combined with a sharp local increase to about 420 kilometers per second in the region of the double nucleus, indicates that the response of the stellar orbits is not simply that of a single central point mass embedded in an otherwise smooth stellar distribution. The depleted core changes the phase space structure by removing many stars on low angular momentum orbits that would otherwise pass very close to the center, while the presence of two closely spaced massive objects alters the shape of the potential creating zones where stars can be temporarily bound to one or the other black hole, or can pass through the region between them on complex three-dimensional trajectories. In a simplified description of the central phase, space stars can be grouped according to the minimum distances that their orbits reach from the center. Those whose pericenters lie well outside the separation of the nuclei interact mainly with the combined potential of the pair and see it as effectively a single massive object. Their orbits contribute to the roughly constant velocity dispersion across most of the core. Stars whose pericenters bring them into the region around the separation of the nuclei feel the details of the binary potential more strongly. Some of these stars are scattered onto higher energy orbits in three-body encounters, while others are deflected onto new orbits that keep them within the inner core but redistribute their angular momentum. These interactions contribute to the local enhancement of the dispersion in the region of the double nucleus. A smaller subset of stars passes very close to one or the other black hole on scales where tides become important. For black holes of several billion solar masses, the radius at which a solar-type star would be tidally disrupted is comparable to or smaller than the radius of the event horizon. So many stars that come within this region would cross the horizon whole rather than being disrupted outside it. This reduces the rate of bright tidal disruption events compared with galaxies that host less massive black holes, even though the central stellar density is high. In a system like NGC 54119, the most important dynamical effect of close passages is thus the cumulative change in the orbits of stars due to repeated gravitational encounters with the binary rather than individual luminous disruption events. The nearly isotropic orbital distribution inferred from dynamical models in the innermost few hundred parsecs shows that stars have comparable amounts of motion in radial and tangential directions. This is consistent with the phase in which the binary has already excavated a core by transferring energy to the stars, but has not yet produced a strong excess of tangential orbits. In such a configuration, many stars still approach the center on orbits with small angular momentum, providing a continuing supply of close passages that can in principle harden the binary. The traxial shape of the galaxy on larger scales adds to this supply, because box orbits and other centrophilic trajectories bring stars repeatedly near the center without relying solely on slow collisional relaxation to change their angular momenta. The cumulative effect of these processes is to maintain a population of stars whose orbits sample the potential in the region of the double nucleus, and to support the observed pattern of high-velocity dispersion there. From the observational point of view, the main signatures of the binary at present are embedded in the stellar kinematics and in the structure of the depleted core. The double nucleus is resolved in the light distribution, but the orbital motion of the two black holes around their common center of mass has not been measured directly. The orbital period expected for a bound pair with a separation of order 70 parsecs and a total mass of about 10 billion solar masses is of order several million years, so any change in the relative positions of the nuclei on human timescales would be extremely small. Instead, constraints on the configuration and mass distribution come from comparing detailed dynamical models with the observed maps of velocity and dispersion. Single black hole models that assume a smooth axis-symmetric core and no double nucleus reproduce the kinematics outside the central tens of parsecs, but fail to account for the strong local peak in dispersion and for the asymmetric nuclear structure. Models that include a massive central object with a total mass of order 10 billion solar masses embedded in a chord stellar distribution, together with a nearly isotropic orbit population match both the core size and the dispersion pattern, and are consistent with the nuclear asymmetry being due to two black holes of comparable mass. The remaining uncertainties arise mainly from the limited spatial resolution, the need to assume a particular parameterization of the dark matter halo, and the degeneracy between anisotropy in the stellar orbits and the exact distribution of central mass. In the central tens of parsecs, the contribution of the dark matter halo is negligible, compared with that of the stars and the black holes, so the primary degeneracies are between the total black hole mass, the ratio of the masses of the two components, and the detailed orbital structure of the stars in the depleted core. Higher spatial resolution spectroscopy improved modeling of the point spread function, and measurements of additional traces such as compact stellar clusters or gas kinematics if suitable. Gases present could in principle refine these constraints. At the level of description accessible with current data, the central region of NGC 5419 consists of a depleted stellar core whose size is comparable to the sphere of influence of a central mass of about 10 billion solar masses, a nearly isotropic distribution of stellar orbits in the innermost few hundred parsecs, a sharp local enhancement of the stellar velocity dispersion, centered on two nuclear light concentrations separated by tens of parsecs, and a gravitational field in which the mass of the black hole pair and the surrounding stars inside the core outweighs any contribution from the dark matter halo on these scales. In the innermost region of NGC 5419, the physical state of the candidate binary of supermassive black holes can be described in terms of its mass separation interaction with the surrounding stars and likely contribution to the broader population of very massive black holes in brightest cluster galaxies. The total mass inferred from stellar dynamical modeling of order 10 billion solar masses, with uncertainties of a few billion solar masses, places the central object or objects of NGC 5419 among the most massive black holes measured in the nearby universe. This mass is comparable to that inferred for central black holes in a small number of other brightest cluster galaxies and massive ellipticals such as those in NGC 4889, NGC 3842, and Homburg 15A, which also show large depleted cores and high central velocity dispersions. In NGC 5419, the large core radius of several hundred parsecs and the substantial stellar mass deficit implied by the difference between the core Sirsic profile and an inward extrapolation of the outer Sirsic law are consistent with empirical correlations that link core size and mass deficit to black hole mass in core ellipticals. When the measured core size of about a few hundred parsecs is placed on these relations, the implied black hole mass falls in the same range as the value obtained from direct dynamical modeling, reinforcing the conclusion that NGC 5419 hosts a central system with a mass of several billion to roughly 10 billion solar masses. The projected separation of about 70 parsecs between the two nuclear light concentrations and the local peak in velocity dispersion in their vicinity indicate that this mass is not concentrated at a single point, but is instead associated with at least two components embedded in the depleted core. The simplest mass partition, consistent with the brightness of the nuclei and with the symmetry of the dispersion field, assigns each black hole a mass of order, a few billion solar masses, though the data permit a range of mass ratios so long as the total remains near the dynamical estimate. The orbital velocity of such a pair at separations of tens of parsecs is large, in absolute terms of order, a few hundred kilometers per second, but the expected orbital period is of order several million years, and the line of sight component of the orbital motion can be small if the orbital plane lies mainly in the plane of the sky. The very low mean rotation velocities measured at the positions of the nuclei combined with the high local dispersion are compatible with this configuration in which the stellar absorption lines are broadened by the range of stellar velocities in the deep central potential rather than shifted systematically by the motion of the black holes themselves along the line of sight. The accretion state of the black holes appears to be very weak in the current epoch. The photocentric nucleus coincides with a compact radio and X-ray source, whose luminosity is orders of magnitude below that of classical quasars, implying that the central black hole there is accreting at a very small fraction of its Eddington limit. The Eddington limit is the luminosity at which the outward pressure of radiation balances the inward pull of gravity for a given mass. For a black hole of 10 billion solar masses, this limit would be extremely high, so the observed low luminosity corresponds to an accretion rate that is far below the maximum steady value. No strong emission is detected from the offset nucleus, suggesting that if a second black hole is present, there it is either inactive or accreting in a radiatively inefficient mode that produces little electromagnetic output. In the absence of a significant cold gas reservoir in the central region, as indicated by the lack of strong molecular or ionized gas emission, in current data the fuel supply for accretion is limited to hot gas from the surrounding intracluster medium and stellar mass loss within the core. This environment naturally favors low accretion rates and radiatively inefficient flows, and is consistent with the observed classification of the nucleus as a low-luminosity active galactic nucleus. From the point of view of energy exchange between the black hole pair and the surrounding medium, the most important channel in NGC 54119 has likely been the transfer of orbital energy to stars through dynamical interactions, which has created the depleted core and heated the central stellar population. Any mechanical or radiative feedback from accretion such as radio jets or winds is correspondingly weak at present. On a statistical level, systems like NGC 5419 contribute to the high mass end of the black hole mass function and to the predicted background of low-frequency gravitational waves generated by the cosmic population of supermassive black hole binaries. Theoretical models that synthesize the contributions of many merging galaxies across cosmic time indicate that binaries with total masses of billions of solar masses in massive host galaxies provide a significant share of the nanohertz gravitational wave background. A pair with a total mass near 10 billion solar masses at a distance of a few 100 million light-years, if it were to shrink to sub-parsec separations, where gravitational wave emission dominates, would generate continuous gravitational waves in the frequency band probed by pulsar timing arrays. However, at the present observed separation of tens of parsecs, NGC 5419 remains in a regime where gravitational radiation is negligible compared with stellar dynamical processes. Current pulsar timing array detections of a stochastic gravitational wave signal at nanohertz frequencies constrain the ensemble properties of many such binaries, but do not isolate the contribution of any single system like NGC 5419. On the smallest resolvable scales, the binary in NGC 5419 thus appears as a very massive weakly accreting central system, with a projected separation of tens of parsecs embedded in a large low-density stellar core, whose size is comparable to the sphere of influence of the black hole mass, and surrounded by a nearly isotropic population of old metal-rich stars whose motions record the depth and shape of the central potential. In a physical description centered on the binary scale, the central region of NGC 5419 can be treated as a system in which a very massive pair of supermassive black holes, with a combined mass of several billion to about 10 billion solar masses, interacts continuously with the surrounding stars of the depleted core, and with the hot gaseous environment supplied by the group and cluster. The stellar distribution inside the core has already been reshaped into a low-density configuration, with a shallow inner light profile and a nearly isotropic orbital structure in the innermost few hundred parsecs, consistent with a history in which previous mergers have brought black holes to the center and allowed them to transfer orbital energy to the stars. The present projected separation of roughly 70 parsecs between the two nuclear light concentrations places the candidate binary at a stage where the pair is well inside the sphere of influence radius, but still far from the regime where gravitational waves dominate its orbital evolution. At this separation, the relative orbit of the black holes is governed by the combined gravitational field of the pair and the surrounding stellar mass within the core. Dynamical friction from the background stars and from any residual dark matter continues to remove orbital energy, but the efficiency of this process is reduced compared with the earlier kiloparsec scale in spiral, because the mass enclosed within their orbit is now comparable to or smaller than the mass of the pair itself. Further orbital decay therefore depends primarily on interactions with individual stars, whose orbits carry them into the region near the binary. In three-body encounters, a star that passes close to the pair can be ejected on a higher energy trajectory, carrying away energy and angular momentum while the binary separation shrinks. The rate at which such encounters occur depends on the density of stars in phase space near the center and on the shape of the gravitational potential on larger scales. In a triaxial system such as NGC 5419, where many stars follow box or other centrophilic orbits that pass repeatedly near the center, the supply of stars available for interaction is larger than in a purely axisymmetric configuration, so loss cone refilling is expected to be more efficient. This supports continued hardening of the binary, even after an extended core has formed, though the exact timescale remains sensitive to details of the orbital structure that are not directly observable. The depleted core itself is a record of the energy exchange that has already occurred. The difference between the observed inner light profile and the inward extrapolation of the outer Circic law corresponds to a stellar mass deficit of several times the inferred black hole mass, as is typical in massive core ellipticals. This deficit can be interpreted as the cumulative effect of multiple black hole binaries ejecting stars during a sequence of dry mergers. If NGC 5419 has experienced more than one major merger, the current binary may be the latest in a series of central pairs, each contributing to the growth of the core. The large core radius, the high central velocity dispersion, and the very large inferred black hole mass all indicate that the galaxy has undergone substantial mass assembly in its central regions, and that the binary at the center is the product of this assembly history. On the scale of the pair, the surrounding stellar population consists mainly of old metal-rich stars with little evidence for recent star formation, so the main source of fresh stellar mass in the core is the slow influx of stars from larger radii and the gradual shedding of stars from disrupted satellites. The hot gas associated with the intracluster medium permeates the larger environment, but has a low density in the immediate surroundings of the binary, and there is no strong indication of a dense cold gas disk or torus that would exert additional torques on the orbit. The weak nuclear activity at the photocenter suggests that the accretion flow onto at least one of the black holes is in a radiatively inefficient low accretion rate mode, and that feedback in the form of jets or winds is modest at present. As a result, the main coupling between the binary and its environment is gravitational rather than hydrodynamical. In the context of models of brightest cluster galaxy evolution, NGC 5419 represents a case where the central black hole system has reached very high mass while remaining in a low luminosity state, and where the imprint of the black hole pair on the host galaxy is encoded most clearly in the structure and kinematics of the stellar core. The binary modifies the distribution of stellar orbits in the central region, shapes the size and depth of the core, and sets the scale of the central velocity dispersion peak. If the pair continues to harden through interactions with stars and any available gas, it will eventually reach separations at which gravitational wave emission becomes the dominant channel for further orbital decay, leading to coalescence on timescales that according to current models can range from less than 1 billion years to longer than the age of the universe, depending on the efficiency of lost cone refilling. Until that stage is reached, the observable consequences remain those of a massive, slowly evolving binary embedded in a cored stellar distribution, a large low-density core with a shallow inner light profile. 2 nuclear light concentrations separated by tens of parsecs, a strong local peak in stellar velocity dispersion, and a nearly isotropic orbital structure in the innermost few hundred parsecs. Within the limits imposed by current spatial resolution and sensitivity, this description summarizes the present dynamical state of the innermost region of NGC 5419 at the scale of its candidate supermassive black hole pair.